So in the previous video, we introduced the functor type class, and before diving into the applicative type class and especially the monad type class, I think it is important to introduce some other function utils, since as we'll learn, both the applicative type class and especially the monads are type classes that deals with computations, and since computation can be expressed using functions, it would be a nice idea to have some other tools to better operate with functions. And one important tool that we have not yet introduced are lambda functions or anonymous functions, which we can declare by using this syntax, which, as we see, requires a backslash and an arrow, much like the one we use in the type declaration. And the way it works is between this backslash and the arrow, we do declare some parameter names that we can then use in some expression that, as we know, will substitute the function. And lambdas are, of course, a way to declare function on the fly. Of course, a better way to declare this function would be by doing something like this, where we do declare the parameters and then use those inside an expression rather than using a lambda. But lambda, of course, are useful in order to define functions that we'll need to use as an example in higher order functions. And exactly for this reason, lambda can be an important instrument from this point of the course on. And this way of declaring this sum lambda function is just creating a function using the lambda. And since function, as we know in Haskell, are first class values, can be stored inside variables. And now this variable is a valid function. And here I'm using as an example a lambda to define our known choose function, just being a little more explicit with what this function is doing. So now that we know what lambdas look like, we'll see how to use them also while using applicatives and monads. And now let's pass to a utility function that is implemented in the standard Haskell, which is the const function. And here, as an example, I've defined a function that I called whatever true. And this function, as we also see from the type, takes anything, and I mean literally anything, but always returns a boolean. And the implementation of this function is just this expression, which is const true. And as always, when we encounter something that we are not sure what is doing, in this case this const word here, we go in the GACI shell and ask for the type of const in this case, and we see that const is a function that takes two arguments and returns the type of the first argument, and not only the type but the actual value itself. So an ideal implementation of the const function would be this one. And const is, of course, a function that takes two arguments, but it ignores the second one and always returns the first. And in this case, this whatever true is a function that, given an x, and x can be anything, returns always true. And if you were to think about this in a mathematical way, you could think this function to be a function that, given an input, totally ignores that input and always returns 1. Another function that is built into Haskell is the identity function. And the identity function, as you can imagine from the name, is just a function that, given an input, returns that same identical input. And you may ask now, well, why are you introducing us these two functions? Well, actually, we'll see some parallelism also when talking about the applicatives and the monad type classes. And let me also show some cool stuff that we can do when we combine, as an example, const and id. And we know that const is a function that always returns the first argument. And if we provide id to the const function, what we get back is a function that has two arguments and returns the second. And this is happening because this expression is evaluated like this. So there is the const function, which is greedy, and taking these two arguments, it always returns the first. So what we are actually executing here is just id 4, and as we know, id always returns whatever it gets. Therefore, it returns the 4 it got here. And we could have actually achieved the same identical result by using another utility function, which is the flip function, with the difference that flip is a bit more generic and the type of the flip is this one. And as we know, in Haskell we only have function that goes from one input to one output, so we can read the type of flip as being a function that, given a function that takes two arguments, returns a new function but with the types flip. And now we understand why the name of this function is flip. And an ideal way to implement the flip function, which uses lambda in order to make clear that by providing only the first argument, what we are returning is an entirely new function. Given some binary function, returns a new function that takes two arguments and then applies those arguments to whatever function we got in the opposite order that they were given. So with this video, we introduced some functions that may or may not turn useful while writing our programs, but most importantly, we saw how to use the lambda notation in order to create functions on the fly. And this will turn useful especially when dealing with higher order functions. In any case, if you find the occasion to learn something from this video, consider to subscribe to the channel. If you really want to support the creation of this content, remember that in the description below there is a link that allows you to delegate your data to Harmonic pool. With that being said, let me thank you for your time. Remember to stay decentralized, and I will see you in the next video. Bye bye.